All right, ladies and gentlemen, I hope you're having a very good Friday. I will have your test grades for you when I see you on Tuesday. But right now, you need to get out these notes, which are your momentum notes that you could have printed off on the web, or you need to get out a piece of paper. Everyone has to have one or the other. You also need to have on your desk a calculator, and the substitute should be giving you the momentum packet. So make sure you get all that organized, and we can pause this until you're ready to get started, but then we're going to get started. As I go through this, I'm going to be moving this little box that's in the top left corner right now that says I'll be moving it around. So just realize that it'll move from spot to spot as we go to different slides. Okay? Well, then let's talk about the big mo and its transfer. Momentum is a physics term, and it refers to the quantity of motion that an object has. A sports team which is on the move, like our volleyball team or our football team right now, way to go, has the momentum. If an object is in motion or on the move, then it has momentum. Some things you need to realize about this is that momentum has to have the object moving. It is mass in motion. So momentum is got to have motion involved. All right. So let's talk some more. Let's look at some examples of what momentum is. Which will have a greater momentum? Me throwing a baseball, and I don't throw a baseball real well, at you, or Roger Clemens throwing it at you? Let's think. Roger Clemens, me. I'm thinking that pretty much the Roger Clemens one. What are you thinking? Well, let's think about why. Why would it be that Roger Clemens's ball is more momentum than me? That is because his is going to have, it's going to take more force to stop his. Because obviously his is going to be thrown more about 95 miles per hour to stop it, and mine might be thrown more at 45 miles per hour, if that. Okay. So even though we'd both be throwing a baseball, which has the same mass, his is going to have more motion to it, and so it's going to have more momentum. So let's continue with some more examples. Which has more momentum? A car at 45 miles per hour or Thomas the Tank Engine at 45 miles per hour? I'm thinking the train. Are you thinking the train? Hopefully you're thinking the train. Well, let's talk about why, because it is the train. So why would it be the train? Because there's more force needed to stop a train than a car. Even though they're traveling at the same speed, the train has more mass. And since momentum is mass in motion, the one with more mass is going to have more momentum. And the train has more mass. All right. So what factors are important for determining the momentum of an object? Well, we've talked about two. So let's think. Forces, factors that are important. Well, it would be mass and velocity. They're important factors when considering the force needed to change the motion of an object. So those are the two main parts. This relationship was originally developed by our own Mr. Newton in his second law when we talk about force equals mass times acceleration. So momentum is the product of mass and velocity of an object. So this is our new formula. So momentum equals mass times velocity. And the way that it looks is they use this funky looking P equals M times V. That's momentum. So let's determine the momentum of a few things. We're going to determine on A, we have a mass of 60 kilograms. We have this halfback, so he's a football player. And he's moving eastward at a velocity of 9 meters per second. So that means he's going this direction. So we want to know the momentum. So we're going to solve for momentum. Oops. So all we're going to do is we're going to put 60 times 9, which is going to be 540. And the units for this is going to be kilograms meters per second. Now, it's extremely important that you realize that these units don't have a squared on them, and this is not a Newton. So make sure that you do not write a Newton for the units of momentum. It is literally kilograms meters per second. Now this momentum is eastward. Okay, so it is one of those things that we could talk about directional information because velocity is directional speed. Okay, so remember that. Now the next one on B, we have a mass of 1,000 kilograms because we're talking about a car, and it's moving northward, so our velocity is up at 20 meters per second. So to find the momentum, we're going to take 1,000, which is our mass, times our velocity of 20, and we would get an answer of 20,000. And this would be kilograms meters per second, and it is upwards. Okay, so it is northern. This one was eastern. So if I go back and box them, that's what I could have as answers. And finally for C, on our example problems, we have a freshman. Oh, we like freshmen, little fishies. 40 kilograms. All right, is their mass. Obviously, they're a little smaller than the halfback on the football team. And the velocity is 2 meters per second, and it's southward, so we draw an arrow down. So when we solve this problem, we take 40 times 2 and get 80 kilograms meters per second, and it would be southward. Okay, hopefully everyone's good with this. If not, pause, take a minute to look at it, and then we can keep going. We're going to take another example, and we're going to say that the car possesses 20,000 units of momentum. So this right here is our momentum. And the question behind this little box says, what would be the car's new momentum if we, so we're going to look for a new momentum, and we need to remember that the formula is, oh, I don't want to use that one. Sorry. Okay, is momentum equals mass times velocity. So we want to say if we double the velocity, so we want to put 2v in there. Well, if we have mass times 2v instead, then that's going to cause our momentum to be double the amount because you multiplied one of them times 2. What about if we triple the velocity? So now we're going to make that 3v. Well, we're still just doing mass times 3v. So now the momentum should be 3 times as much. I always draw those p's funny, sorry. And then if the mass were doubled by adding more people, then that would be like saying 2m. So we'd say 2m, but we'd keep the same velocity. So 2m times velocity would give us now 2 momentum. So it's going to double my momentum. And if both the velocity were doubled, so 2v, and the mass were doubled, so 2m, what's that going to do to the momentum? Well, if we have 2v times 2m, 2 times 2 is 4, so that's going to be 4 times as much. All right. So again, these would be those kind of things that if I had 20,000 units of momentum on this first one, it would have now been 40,000 units of momentum. On B, we would have had 3 times as much, so that would have been 60,000 units. And on C, it would have been 40,000 units. And on D, we would have had 4 times as much, so it would have been 80,000 units if I wanted actual answers each time. All right. So really all I did was just manipulate the formula and then go back and solve for a new momentum. Okay. So an object's momentum will change if its mass or its velocity changes. If either one of those change, then momentum is going to change. What most common is a change in velocity. What do we typically call a change in velocity? Can anybody remember? Come on, somebody say it out loud. It would be acceleration. If you said acceleration, you are so smart. You're super smart. okay, which we know is the change in velocity over time. All right. So according to Newton's laws, a net force causes an object to accelerate or change its velocity. So net force was a change in velocity. So Newton's second law said F equals ma. Hopefully everybody remembers that, considering we just had a test on it. Which another way I wrote that would have been m times the change in velocity divided by the change in time. I did that. And I could also just say that it was this, mass times the delta V divided by delta T. Now, if I put the beginning formula, this one, and this F next to each other, I can rearrange the formula to look like this, so that it's F times the change in T equals m times the change in velocity. So the change in momentum equals what we had said earlier was this, but we can also say that momentum equals that. Okay, so force times the change in time. Now that's known as impulse. Okay, so impulse equals a change in momentum. So force times the change in time is also known as impulse. So what does this really mean? Well, it means that if we have a car that's 1,000 kilograms and it's moving at 30 meters per second, which means it has a momentum of 30,000 kilogram meters per second, it can be stopped by 30,000 newtons of force acting for 1 second, because those would be equal to each other, because force times time would be 30,000 and 1,000 kilograms times velocity would be 30,000. So that's what that means. Or 3,000 newtons of force acting for 10 seconds, which is a normal stop. That would also tell us that we have the same momentum. All of those things are equal to each other. All right. So let's talk about the carts. We have a 0.5 kilogram cart, which we're going to call number 1. Oops, sorry. We're going to make it blue. Okay. Number 1 is going to be blue. Number 2 is going to be red. All right. So we have a mass of our first cart to be 0.5 kilograms, and we're told that it has a force of 1 newton, and it has a time of 1 second. For our number 2 cart, which we're going to say is red, we're going to say our mass is 0.5 kilograms, and we have a force of 2 newtons and a time of 0.5 seconds. Okay. Our first question that they want us to answer would be, which one has the greatest acceleration? Well, to solve for acceleration, we're going to say force equals mass times acceleration, or acceleration equals force divided by mass. So for our first car, we're going to say 1 divided by 0.5, which equals 2, if you're doing this in your calculator, meters per second squared. And then we're going to do it for our red one as well. So we're going to take our force, which is 2 newtons, and divide it by 0.5, which is 4 meters per second squared. So when we have to answer the question, which one had the greatest acceleration, we could say that it was cart number 2, because it has more force. All right. So let's keep going. See what else it asks us. Okay, I'm gonna have to erase. Sorry. Let me erase all this other stuff. Forgot that I had all this in there. Da, 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 da. Okay, so we said it was number 2, and it was because more force. All right, because we had a force there, and we had a mass there, and we have a time there. And then we had a mass there, a force there, and a time there. All right. Now it also has which cart, number 1 or number 2, has the greatest impulse? Well, remember that impulse is going to be force times the change in time. So if that's the case, I'm going to say that the force for 1 is going to be 1 Newton times my change in time, which is 1 second. So that's just going to be 1, and that is kilograms meters per second, because it is momentum also. All right. And then for the second cart, we're going to say that it is 2 newtons of force times 0.5 seconds, which is also 1 kilogram meters per second. So does either cart have a greater impulse? Hopefully you said no, because you'll notice that they both have the same. All right. Because the second cart has more force, but it took less time. Okay. So then on C, it says which cart, 1 or 2, has the greatest change in momentum. Well, if you remember, we said change in momentum equals impulse. Those things, if you look at the previous slide, are equal to each other. So again, which has the greatest? Neither, because they are the same. So our answer here will be neither, because they have the same. All right, let's keep moving. Rhonda. Rhonda has a mass of 60 kilograms. So we could write that down and say that her M is 60 kilograms. And she's riding at a 25 meters per second. So that would be a velocity. 25 meters per second. Ooh, and she has a sports car. And she has to suddenly slam on the brakes to avoid hitting a dog. I'm glad, because, I'm not all about hitting animals, okay? So she strikes the airbag. Oh, that's not very good at all. And she brings her body to a stop. So that would be a second speed we have. So that's going to say her final speed is 0. And her initial speed is 25. And she does this in a time of 0.4 seconds. It says, what average force does the seatbelt exert on her? All right. Well, force equals mass times acceleration. And for this one, we're going to say force equals mass times Vf minus V naught over T. Okay. So we're now going to have 60 times 0 minus 25 divided by 0.4. All right. Hopefully someone's plugging in their calculator this information. And you should get an answer of a negative 3,750 newtons. Now, this is the force that she applies. So what is the force that the seat belt exerts on her? Hopefully I'm hearing opposite but equal. So it should be 3,750 newtons. All right. So then the next question is, if Rhonda had not been wearing her seatbelt, that would have been really bad considering it's a law now, and not had an airbag, super bad, then the windshield would have stopped her head in a time of 0.001 seconds. That's really fast. What average force would the windshield have exerted on her? So instead we need to say 60 times 0 minus 25, but instead have 0.001 as our time. And when we do that in our lovely little calculators, which all of you are doing right now because y'all are so good, we would find out that hopefully someone is hollering that it would have been 1,500,000 newtons, which is a ton more than we had just a minute ago. Okay, so that's why seatbelts are super good for you, because it takes a longer time to stop your body versus if you run into the windshield. Okay, so some applications of impulse. Let's talk about that. Contact time is reduced if the arm's deceleration is kept as small as possible. So that would mean when we don't touch it very long, the arm's deceleration is kept really small because we keep going. All right. This is done by using follow through, which means that we continue to push during the contact period. So the force is still being applied. We aren't like stopping the minute we touch it. So that's an application of impulse. Also, we could say if we hit somebody, you can spread impulse out over a longer time, and that would mean that the force is less. So if we hit somebody and it takes us a long time and we make contact for a long time, then it's going to be softer. Or either way, the change in momentum of the boxing glove or the fist or the arm will be the same. All right. So if we make the force more, then and we do it in the same amount of time, it's going to be harder. Okay. If we make the time longer, but the force is the same, then it's going to make the force less. Okay, so we're going to have the same change in momentum, but one of the two is going to change. All right, so more force, same time, it's going to be a harder hit. Okay, but you have the same amount of momentum. So observe that the greater the time over which a collision occurs, the smaller, so some words I want you to highlight, greater the time over which a collision occurs, the smaller the force acting upon the object. Thus, you minimize the effects of the force involved in a collision. This is why you want it to take you more time to actually slow down. All right. The time must be thus, to minimize the effects of the force on an object involved in a collision, the time must be increased. And to maximize the effects, all right, and maximizing is bad. We don't want to maximize effects typically, unless we're wanting to hit somebody really hard. To maximize the effects of force on an object involved in a collision, the time has to be decreased. Okay, so notice that's why we have large bumpers and it takes a long time, hopefully, for collisions for us to actually get stopped versus the impact if it's really fast. Okay, so I think one of the next couple of slides shows that. This one, okay? If we just hit a wall and instantly come to a stop, we have momentum, but that gives us a really large force. The impulse ends up being really tall. But if we run the truck through hay, for example, it's going to take a really long time to get through that, and so the momentum is going to be different. Okay, it's going to minimize it. So I want you to switch gears a little bit. And now that's the notes pretty much for this unit. And you should have the packet, the momentum packet, in front of you. And a lot of that is stated in that packet as well. And it talks about how we can talk about impulse. And it shows you some solved example problems. But I would like to do practice exercises 1 through 6 with you. So that's why I want you to have your lovely little calculators and things like that. So take some time, get organized real quick if we need to pause again so that you can get everything together. Make sure you have your calculator and all that fun stuff. Practice exercises number 1. On April 15th, 1912, the luxury cruise liner the Titanic sank after running into an iceberg. What momentum would the 4.23 times 10 to the 8th kilogram ship have imparted to the iceberg if it had hit the iceberg head-on with a speed of 11.6 meters per second? Actually, the impact was a glancing blow, so it wouldn't have quite been that much, but we're going to calculate these numbers. So we are doing exercise number 1, and we know that we have a mass of 4.23 times 10 to the 8th kilograms. And we know that the velocity of the cruise ship was 11.6 meters per second. And they want us to find the momentum. And I want to change that, sorry. Momentum. So we know that to be mass times velocity. So 4.23 times 10 to the 8th multiplied by 11.6 would give you an answer of. Now, if we're plugging this in our calculators, remember we do not hit times 10, ladies and gentlemen. We hit 4.28, and then we hit the lovely little EE button. Oh, sorry, 3. Sorry, I'm typing the wrong numbers. 4.23 EE, and then we type in the power 8. You never hit times 10. And even if you have a graphing calculator, you should be taking care of this. Multiplied by 11.6 equals. You get this really gigantic number in my calculator. So I want you to hit second and 5, and that'll put it in scientific notation, which then you should write 4.91 times 10 to the 9th power. Now, since this is momentum, the units would be kilograms meters per second. And that would be the answer to A on this problem. It says, if the captain of the ship had seen the iceberg a kilometer ahead and had tried to slow down, why would this have been a futile effort? Okay, it would have made little difference because when you think about it, even if the speed, if this number right here, guys, had been smaller, is it really going to make a difference when you have this large of a mass? I'm going to tell you no, it won't. All right. So because the mass was so large, it would have been pointless. It would have been pointless. Might not have been pointless, but it wouldn't have helped a lot. All right. So that would be your answer to B. And that finishes exercise 1. So turn the page on your packet and go to exercise 2. All right. Exercise 2 says auto companies frequently test the safety of automobiles, thank God, by putting them through crash tests to observe the integrity of the passenger compartment. If a 1,000-kilogram car, okay, that would be our mass, 1,000 kilograms, is sent towards a cement wall with a speed of 14 meters per second. Okay, so now we have a speed of 14 meters per second, which is velocity. And the impact brings it to a stop, so we have another velocity. All right. In 8 times 10 to the negative 2 seconds, so there's a time. 8 times 10 to the negative 2 seconds. With what average force is it brought to rest? Okay, well, we need to think about this. We know a little bit about, okay, say force, or we could say this is our initial, and this is our final. Okay, so we know force equals mass times acceleration. We could also say that Ft equals the mass of our final velocity minus our initial velocity. So we could say those things. And if we say that, that's really just saying F equals m times Vf minus Vo over T, right? So we can say 1,000 times my 0 minus 14 divided by 8 times 10 to the negative 2. Okay, do your calculations. Have your calculators in your hand. All right. So now we're going to say 14 negative divided by 8 EE negative 2 equals multiplied by 1,000 equals, and we should get, and I'm going to take my calculator out of scientific. How do I do that? All right, if your calculator is still in scientific notation and you want to take it out, you can just hit second 4, and that'll take it out of scientific notation. But you should have an answer of a negative 175,000 newtons. Now, this is the average force of how it's brought to rest. Remember, the negative sign is telling us directional information. So if you didn't have the negative sign in that, that would be okay. But since it's bringing it to rest, it's actually going against what the forward motion of the car was. All right, moving on. Number 3, exercise 3. Rhonda, who has a mass of, oh, we did this one. It was one of our examples. Okay, so we're not going to do that. How many times? So we can do the first one, and we found out on our previous example in our PowerPoint that our mass was 60 kilograms. We'll go ahead and fill it out. That our initial speed was 25 meters per second. that our final speed was 0 meters per second and that our time was 0.4 seconds. So we found force equals mass times Vf minus V naught over T. We plugged in our numbers and found out that it was 3,750 newtons for the first part. For the second part, it was 1,500,000 newtons if the windshield instead. And then it asks you on C how many times greater is the stopping force of the windshield than the seat belt. Well, you take that 15 or 1,500,000 and divide it by your 37 or 3,750. I do know how to talk. And when you do that calculation, you should come out to be that it's 400. So it's 400 times larger. And those are your three answers, A, B, and C. Again, okay, because our second time for our windshield was 0.001 seconds. All right, so we keep moving and we'll do number 4. Remember, if at any time y'all need her to stop the, what am I talking about? If we need to stop the notes or pause the notes, we can, and then y'all can catch up. So exercise 4, we have 270 million people in the United States, and they all jump up in the air simultaneously. That would be fun. Okay, pushing off the earth with an average force of 800 newtons, each for a time of 0.1 seconds. What would happen to the 5.98 times 10 to the 24 kilogram earth? Well, we know that the force is going to be 800 newtons, but we need to multiply that by the 270 million people, which, believe it or not, is 2.7 times 10 to the 8th power, ladies and gentlemen. Okay, and that's our actual force. We know that the time involved is 0.1 seconds. And we know the mass of the Earth is going to be 5.98 times 10 to the 24th kilograms. If that's the case, we could actually find acceleration and see if it's going to do anything to the acceleration of the Earth. Because we can say Ft equals ma, because impulse equals the change in velocity roughly. Okay, so this would be change in velocity if you want to look at it that way, which is really a. Okay, so we would take our values, which are my 800 times my 2.7 times 10 to the 8th power times my time of 0.1, and then I'm going to divide that by my mass of 5.98 times 10 to the 24th, and that's going to give me my change in velocity that this is going to cause, or my acceleration. Okay, it's not actually acceleration. I can't say that because I don't have the time involved anymore. It's just the change in speed. I need to fix that. Sorry, guys. It is just a change in speed because we moved the time over. All right. So when you calculate that, we have our 800 in our calculator times 2.7 EE8 times 0.1 equals divided by 5.98 EE24 and equals, and we get a really small number, which would be 3.61 times 10 to the negative 15. And this is meters per second. That's the speed that the people are going to affect the Earth with. Okay, this speed is minute, so believe it or not, it says the question was, what would happen to the Earth? Nothing. That would be your answer. Nothing. Because this is such a small number, because such a small speed would not change Earth's motion. Hopefully y'all are all getting this down. Are you getting this down? Okay. All right. So that's really your answer is nothing because such small speed would not change Earth's motion. Moving on. Two more problems. All right. We have exercise 5. In Sharky's Billiard Academy, Maurice is waiting to make his last shot. He notices that the cue ball is lined up for a perfect head-on collision as shown. Each of the balls has a mass of 0.08 kilograms. The cue ball comes to a complete stop upon making contact with the 8 ball. Suppose Maurice hits the cue ball by exerting a force of 180 newtons for 5 times 10 to the negative 3 seconds, and it knocks head-on into the 8 ball. Calculate the resulting velocity of the 8 ball. All right, so we have a force of 180 newtons. We have 0.08 kilograms. That would be a mass. And we have 5 times 10 to the negative 3 seconds. That would be time. We want to find a resulting velocity. All right. So we use the formula F triangle T equals M triangle V. And we're solving for the triangle V. So we're going to say 180 times my 5 times 10 to the negative 3 divided by my 0.08. And we'll type that in our lovely calculators. And anybody got an answer? Ooh, that sounds correct. I don't know. Okay, if you had 11.25, then that would be that you are super smart because that's the correct answer. And we would have meters per second as the units because it is a velocity. All right. Okay, final problem, exercise number 6. Exercise 6. During an autumn storm, hope we don't get any of those, we have 0.1012 kilogram hailstones traveling at 20 meters per second, and they make a 0.2 centimeter deep dent in the hood of Darnell's new car. I bet Darnell is upset. What average force did the car exert to stop the damaging hailstone? All right, things we know. We know mass is 0.012 kilograms. We know a velocity of 20 meters per second. We know another velocity of 0 meters per second. We also know anything else? Oh yeah, we know distance is 0.2 centimeters. Well, key here. We are not allowed to use centimeters, ladies and gentlemen, so we have to convert. So we divide this by 100 to get it into meters, and that gives us 0.002 meters. Okay, so make sure you remember that. All right. So, let's look. We want to find, we're asked to solve for force. Yes? Okay. The first thing I'm going to have to do is find some time here because I'm going to need to look at the fact that if I have Ft equals m change in v, okay, then I'm going to have to realize that I have to have a t somehow. Well, I can find an average velocity. Average velocity would be taking my two velocities and dividing them by 2. So 20 plus 0 divided by 2 would be 10 meters per second. That's an average velocity, yes? So if I take an average velocity, I should be able to find an average time that this all occurred in, because time would be distance divided by velocity. And again, I'm going to use my average velocity to find my time. So I'm going to say that I went a distance of 0.002 in, and I had a speed generally of 10 meters per second. So you should be able to find out that this all took place in a matter of 0.0002 seconds. If that's the case, we now have time. So to solve for force, if we use this down here in our formula for time, we're going to solve for force by saying our mass times our velocity change. And what was our velocity change? It was a positive 20, okay? Our change in velocity divided by time. So we're going to say our 0.012 times our change in velocity, which is 20. And then we're going to use our time, which is 0.002. And when we type this in our lovely little calculator, 0.012 times 20 equals divided by 0.002, we should get an answer of 120 newtons. All right. Ooh, I didn't do that right because I left out a 0. Oh gosh, come on, Miss C. 0.0002. Hopefully somebody corrected that and I just didn't hear you. Sorry. Okay, so that would make my answer not 120 but 12,000 or 1,200 newtons. Okay, that should be the correct answer. Sorry. All right, by doing these example problems now, you should be able to do the additional problems, which are at the back of this packet. Now, the additional problems, remember, have an A in front of them. And y'all need to do additional problems 1 through 6. You should be able to do those 6 problems since we did these 6 problems and they're very similar to each other, so you have examples to look at. And you need to do them on a separate sheet of paper. I do not mind if you work together, but you should be able to finish them by the end of class. That way you won't have any homework. Yay, no homework in physics. But if for some reason you don't get them done, which you should get them done, then you can have them ready at the very beginning of class on Tuesday. But I want them due at the end of class, okay? So get busy and get it done so you have no homework in physics. All right? You guys have a great weekend, and I'll see you Tuesday.